Plane tessellations. Ooh, big words, big words. Now this one is more of a slideshow type lecture, and it will eventually lead us to our fourth portfolio assignment question. So, first there are some concepts and words to understand, like what is a tessellation. But we can see, if you look around, often in floor tiles and things, you see interesting patterns of how different shapes are put together to fill the whole floor. Could be a variety of shapes that would be able to achieve this. You can get more interesting patterns and shapes, but we are going to keep things very simple. You also see this concept in nature. The hexagon is used to fill a surface. The sort of similar shapes on the shell there are used to fill that surface. So, typo there, I apologize, I put my hand over it. No. Somewhere there will be a typo. Just wait for it. Tessellation is a perfect covering of a flat surface, the plane, made up of repetitions of some regions or figures or shapes, and we'll focus on basic shapes. There can't be any overlapping. There can't be any gaps. Then it is a tessellation. Now we're only looking at plain, flat surface tessellations. So we won't say plain tessellation every time, because it's the only kind we're going to look at. We'll just call it a tessellation. So if I'm able to use whatever shapes I have and cover the surface with no overlapping of the shapes, no gaps between them, that's a tessellation. Sometimes I can use just a single shape. Sometimes I use multiple. But we then say those shapes or that shape tessellates the plane. If I'm able to do this. Tessellation. Now, if I look at that picture, which polygons, which shapes are used there? It has a three-dimensional look to it. And it looks like they are cubes. But they're not cubes. They're just differently shaded parallelograms. And by the shading, it can create interesting effects. Making it look three-dimensional in this case, or whatever.
Cuber.
So, that's one parallelogram. By coloring it differently, it certainly works. Actually, they might not be exactly the same. I think they are. Can any parallelogram work? Can any parallelogram tessellate the plane? What do you think? You can't dwell on it too long, because if you just look further in your book, you have the answer. There's my parallelograms. So by stringing the parallelogram together on the left there, I'm just making rows that I can easily just stack, or columns in this case. And it doesn't matter which parallelogram I'm using, they will always go together to make sort of a straight bar. But by coloring them differently, I can have interesting effects. Still one parallelogram. So our main objective is to explore another kind of symmetry by way of these tessellations. Starting with simple figures. Yes, like in that diagram, I can have a more complicated kind of tessellation by making the shape more complicated. And there's really no end to what is possible. But in order to get an idea of how this works, I'm going to start with basic shapes and see what kind of simple basic shapes can tessellate the plane. Why does it work? Why doesn't it work? And then later on, how do I make more interesting tessellations? What are some common methods that I can use? So we start with the simplest shapes. In this case, maybe a square. A square can very easily be stacked and tiled to fill the surface. So any square tessellates the plane. And you see it often, bathroom tiles and all kinds of things. And a small step forward from that is a rectangle. I can arrange the rectangles in a variety of ways, but if you just look around, you see rectangular tessellations very often. Very often. So any rectangle will tessellate the plane as well. Stop me if you have any questions or comments. We've discussed the parallelogram, which can be made to look more interesting, but it's still one parallelogram that tessellates the plane. Now, the triangle. Can any triangle tessellate the plane? If I think of my favorite triangle, and I make a bunch of copies of that triangle, can I arrange them to fill the table, if I have enough of them? Do you think a triangle, any triangle, will necessarily tessellate the plane? Without looking in your book, of course. Why and how do I do it? I know you.
Well, no, I just figured like if you have a scaling with like all even sides, you just match up the even sides.
Even a weird one, it's less obvious to me, the one on the right there. Not that it's weird, I don't want to discriminate against triangles. But even a less familiar one, it's maybe hard to imagine. But if I take a triangle like the blue one, and I flip it over along an edge, I've created a parallelogram. And a parallelogram tessellates the plane, therefore triangles will as well.
So any triangle mirrored will make
Any triangle mirrored will make a parallelogram. And because of that, it's always going to work. There might be other convenient triangles to arrange in other ways, but this way will always work. So any triangle works as well. So now we have a bunch of shapes. Triangles, squares, rectangles, parallelograms, therefore rhombuses. So if I have a quadrilateral in general, will that always work? Now there's a website you can go to, if it still exists, I think it does, that shows that, let me see if I can zoom in. I'm going to move this down. It's hard to see. You can sort of see it, yeah. By just flipping the quadrilateral in a specific way, I create those four together. So around this center point, there are definitely no gaps or anything, so that's a perfect fit. And then if you look at the bottom edge and the top indentation, those four as one piece can be pieced together as well. You see the left indentation is exactly the same as the right side, so I can piece them together. So any quadrilateral is going to work.
So
less obvious, but yeah.
if you had one of those, could you just use like translation, reflection, and rotation to achieve what you need?
It is not a rotation.
Did you
It's a bunch of
The bottom
reflections.
left and the bottom right, isn't that just rotated like 180 degrees over though?
Oh, right, because of the multiple reflections.
And then the top
Right.
one is a reflection, and then the top right one.
I
is
tend
translation.
to think of it just as a reflection on each of the edges.
Oh.
Yeah. But yeah, sure. A couple of reflections could be a rotation. Is that zoomed out enough? I think that was. Now, let's make it simpler in another way. Okay, so any four-sided shape is going to work, but there's still a lot of variety within that. If we're going to make it bigger, we need to make the structure a little bit more specific to get a handle on this. So let's go and only look at regular polygons. What is a regular polygon? I haven't given back the quiz, so no one can confirm they know what a regular polygon is.
Equal angles, equal sides.
Everything's the same. It's as balanced and symmetric as you can think. Equal sides, equal angles. Those are the only things there, so everything's equal. That should be equal. Regular is the most important of the polygons because it's the simplest. Having that balanced shape means I can rotate it from every side, it's all the same. So it's the easiest to work with when I ask a tessellation question. So if I now stick to regular, so equilateral triangle, yeah, we already know that because all the triangles work. Regular quadrilateral is a what? The square. And we already know those work. So next up is the regular pentagon, and then hexagon, and so on. Which of those, if I increase the number of sides, will be possible? Well, we don't just want to memorize which ones work, we want to understand why. So that the memorization, if that fails me, I can figure it out. So, we have an n-sided polygon. Now they're going to get bigger, so they don't all have names. So I'll call it an n-gon. If I take any n-gon, be it 4, 5, 6, or whatever, I can split it up into triangles. I can split it up into a certain number of triangles. The square will be split up into 2 triangles. The pentagon will be split up into 3 triangles. That's not the only way, but one of the ways. The hexagon will be split up into 4 triangles. So the number of triangles is always 2 less than the number of sides of the polygon that I'm working with. So a 10-sided polygon will be split up into how many triangles? 8 triangles. Always 2 less. You could do it, but the pattern is always the same. So if my polygon has n sides, then my number of triangles will be n minus 2. But the sum of the angles of a triangle is 180 degrees. So if I have n minus 2 of them, all the angles in here, let's look at the square. I have the top triangle, this angle, plus this angle, plus this angle, these 3 will be 180 degrees. But because I have 2 of them, if I want to add up all the angles inside the square, by looking at one triangle at a time, I just have to count them for one triangle and then multiply with how many triangles there are. So So because the sum of the triangles, because the sum of the angles in a single triangle is 180 degrees, the square has two of them. The sum of the angles in the square will be 2 times 180 degrees. The sum of the angles in the pentagon will be 3 times 180 degrees, because there are 3 triangles. Each triangle contributes 180 degrees. So because triangles are so well understood, I can use them to figure out the angles, and in this case, the sum of all the interior angles of any polygon. The hexagon, sum of all the interior angles, will be 4 times 180 degrees, because there are 4 triangles. Each triangle contributes 180 degrees. Okay, let's make this a little bit more specific with a table over here. Let me zoom in for a second. I think that's, yeah.
So why are you figuring out the...
We're going to get to that. Forget the top now. Let's look at the table. The table is a little late in the slides. So, I have a single triangle, then a square, then a pentagon, hexagon, and so on. These should list some of them. I have a way to calculate the sum of all the interior angles by way of the triangles. So for example, the regular octagon will have how many triangles? 2 less, so 6 triangles. 6 times 180, 1080 degrees. I can use that in combination with the actual shape to know what is the size of a single angle of that shape. So if I look at the triangle, they add up to 180 degrees, but because it's regular, everything's the same. It has 3 angles, so 180 divided by 3 gives me my 60. The square, by way of the triangles, I add up all of those and get a total of 360 degrees for all the angles together, but because it's a square, there are 4 of them, so dividing that by 4 gives me 90 degrees, which I know the angle of a square is 90 degrees. But I don't know the pentagon, for example. The pentagon has 3 triangles inside it, so 3 times 180, 540. But the pentagon has 5 interior angles, because penta means 5. So 540 divided by 5 gives me the size of a single interior angle of a pentagon as 108. And I can then do this for all of them. Any questions on how that right column is calculated? Get the total of all of them first by sort of taking a triangle side root. This one. I don't know what the pentagon angles are. I don't have a pentagon to measure. I just want to calculate it. By way of counting triangles, I can find the total of all the angles.
And then you divide it by...
And then I divide by how many angles there are, because I know the shape. Not by how many triangles, because I'm specifically looking at the pentagon's angles, this whole angle where the hand is. And there are 5 of them. Because it's regular, I know they're all the same, so I can divide by 5. And I can do that for any number of shapes, of course. So, the sum of the interior angles of a regular pentagon, looking at the triangles, I get 540. There are 5 of them in a pentagon, so 540 divided by 5 is 108. And I get the interior angle of a regular hexagon is 120. Interior angle of a regular octagon, 135. And I can keep going. Now, why is that important? Because in a tessellation, if I'm trying to piece these copies of the single shape together, they're going to come together at a point, and their vertices are going to have to meet. If I look at the pentagon, if I'm going to piece them together without any gaps, the interior angles have to add up to 360 degrees all the way around. The pentagon won't work because its interior angle is 108. And if I piece them together, I'm going to get a little gap. It's not going to work. Because 108 plus 108 plus 108 is not exactly 360. I have a little gap missing, and that gap is too small to squeeze another pentagon in. So a single pentagon, copies of that, cannot be tiled to fill the plane without any gaps. So a regular pentagon does not tessellate the plane because of what that angle is. It doesn't fit all the way around and leave no gaps. So the angle has to add up to 360.
So any shape that their merge points add up to 360 will tessellate?
Yeah. Any shape, regular, for now, where the interior angle, or multiples of them, will eventually give me 360, will work. So if I look at the table here again, that's why the triangle works. Because its interior angle is 60 degrees, and 6 of them will make a full 360. That's why the square works.
That's why soccer balls use pentagons,
Well,
because they wrap around.
sure, but once I go 3 dimensions, it's a little different. But yeah, it's not all, it's pentagons and hexagons mixed together, right? It's not just pentagons, I think. Isn't it a mix?
I don't know, I'm just, that's
I can't picture a soccer ball right
the only
now.
one I can think of.
I think it's a mix of 2 shapes. But anyway, the square interior angle is 90 degrees, 4 of them will leave no gaps when I tile them together. Pentagon doesn't work. Hexagon, 120, I can put 3 of them together, and that's going to make 360. And then the octagon doesn't work. And once I go too big, none of them will work. None of them will work. And it turns out the only regular polygons that tessellate the plane is a triangle, a square, and a hexagon. There is nothing else. There are only 3. There are only 3 what we call regular tessellations. Because once my shapes are too big, I have no chance of even piecing 2 of them together. Well, always 2, but not 3. The square, the square has a gap. The gap for the octagons pieced together is very nice for a square, but for a regular tessellation, I'm requiring a single shape, copies of that single shape. And that 90-degree gap is not enough for another octagon to fit. So it can't be done. There are only 3 regular tessellations. 3 regular tessellations. Any thoughts or questions so far? Yes.
So if you said it does tessellate if the interior angles add up to 360 degrees,
Yes.
but then if you, for an octagon, the sum of the interior angles will, like if you keep adding 360, it
No, the
doesn't-
sum of the if I look at page 101,
Yeah,
the sum of the interior angles of the octagon is 1,080.
yeah.
Too
Isn't
big.
that a derivative of 360?
That's way too big. I can't overlap, right?
Right, okay.
So if I piece them together around and around, I can't go over 360, now they overlap.
Right, okay.
I have to meet 360 perfectly. If I'm short, there's a gap. If I'm over, there's an overlap, and neither one of them is allowed.
Okay.
So it has to be perfect. Not that I don't have other options, but for this extremely strict requirement of having one single shape to tile a whole surface, only the triangle, square, and hexagon are allowed. The bees figured this out already. Hexagon works. They know everything. All right, so let me actually, whoops, that's not what I wanted to do at all. Make a little note here. I think that would work if I just try and type on top of this. Can I do that? Can I do that full screen? I cannot. I want to. I can't make it full screen and type at the same time. Okay. So we want to give, so we can represent these tessellations in different ways. One way is certainly draw the picture. There it is. It works. You go all the way around, no gaps, no overlaps, perfect. Another way is to name the tessellation in a way that gives you the instructions for how the shapes or how many shapes there are around a single point. So that the name, if you read the name, you would be able to draw the tessellation. Okay. So the simplest way to do this is to use a number for each polygon. So a triangle has name 3, obviously, because it's a 3-sided polygon. A square will have name 4, pentagon 5, and so on. So there's no issue with what each number's polygon is. So if I, for example, want to name the tessellation of a square, I could say what shapes and how many of them occur around a single point. So the name of a square is 4. Then I put a dot to indicate there's another one. Then I put a dot to indicate there's another 4, another square, another square. So the each 4 represents a square, and the list of 4 of them means there are 4 squares joined at a point. So I read 4.4.4.4. That we call the vertex figure name for a tessellation. Let's put it over here. Vertex figure name. Only if the tessellation works, of course. So a hexagon, I'll squeeze it up here. A hexagon's name is 6, and there are 3 of them. Not ominous at all. Triangle's name is 3, and there are 6 of them. 6. So it's just the simplest, without making a fancy rule for names or other words. There is a more symbolic way to give the reader instructions for how to design the tessellation. What shape and how many of them should be pieced together at a point. There's of course a short way to do this because this looks very similar to multiplication. It is not multiplication, but it makes me think of multiplication. And repeated multiplication is exponents. So I can write this. Now, I don't know if I can write this with this limited tool. We're going to try. 3 is the number. I'm going to squeeze it up here, make it super small. There we go. And there are 6 of them. There we go, that works. That is not 3 to the power of 6. It is not a calculation. It is simply, it's not a, it's simply the most convenient naming system we can come up with without making new things. So the long one or the short one, either way, it tells me 6 triangles go together at a point. And I can do the same for the squares. I can put a 4 with a little 4 at the top. It's not 4 to the power of 4. Just a short version if there happen to be a lot of these 3s together. Still, there are only 3 tessellations. Any questions on the vertex figure name? Because once we go one step further and multiple shapes can happen, then I need to know which ones and how do they stack around a point. Vertex, figure, name. Thoughts? Questions?
You're right about the soccer ball, pentagons and hexagons.
Pentagons and hexagons. Oh, yes. I'm going to have to close this. Maybe, I think the actual soccer ball these days is a mix.
Yeah, it's white hexagons and black pentagons.
There you go.
It's a truncated icosahedron.
Whoa, you're saying names that scare us. Don't say names that scare us. Okay, now one step up. Only one more step up, then we stop. We're not gonna, well, one thing at a time. 2 dimensions for now. So, how would I make it more interesting? By allowing different shapes. Still keeping them regular. Keep them as simple shapes as possible. Everything balanced, everything nice, regular. But I'm allowing for different polygons in the same tessellation. So then I call it a semi-regular tessellation. Regular tessellation, one shape. Copies of that, only that shape. Semi-regular tessellation, I can have 2 or more types of regular polygons. And the only way it's going to work is if they have the same side length, but that's not something I need to really worry about. And on top of that, each vertex has the same pattern around. So a vertex is a point where they meet. So that over there, where the hand is a vertex. Any other point where shapes meet will look exactly the same as another. In the blue. So if I look at any vertex, I see 3 triangles and 2 squares. Any other point, 3 triangles and 2 squares. Maybe it's flipped around, but it's still 3 triangles and 2 squares. 3 triangles and 2 squares. 3 triangles and 2 squares. They're all the same. Which means if I describe what happens around one point, it describes the whole thing. Because they're all the same. They're all the same.
And all those points still add up to 360.
They have to. So let's check. 3 triangles, each one contributes 60 degrees. That's 180. Plus another 90 and plus another 90, 360. But because I'm allowing multiple shapes, I have more options for how to do it. The requirement is still that around a single point, the angles of the shapes I'm using have to add up to 360 perfectly. So the vertex figure name for these guys, let me zoom out, maybe like this. I'm going to have to type again. Let's scroll down a touch. Not too much to show the next page. There we go. Let's zoom in a little bit. Vertex figure name for the blue one. Oh, that's too big. What would you say is the vertex figure name for the blue one? Now, there's good news in that it doesn't matter which point you choose. It doesn't matter where you start, as long as you go all the way around. So if I, for example, look at this top one, look at this one, you can start with the square and say a square is a 4, then there's another square, then there's a triangle, then there's another triangle, then there's another triangle. So that's a vertex figure name. I could have also said, maybe let's type it up here. I could say, oh, let's look at this triangle. That's a 3. Then another triangle. Then another triangle. Then a square. Oh, whoa. Just 4. Then another square. So this can sort of be looped around it's really going around, right? Even though I'm writing it in a row, the last 4 and the first 3 are really connected again. And I can start writing that circle 3, 3, 3, 4, 4 anywhere I want. It's all the same. Yes?
It's typically written as like 3 and then the smaller 3 and then 4 2.
So I can group the 3 3s together if I want to, but it's never going to be that long for us. So to avoid confusion, maybe just write them out. But yes, there is the condensed version in this case as well. So I can have 3 3s and 2 4s. So it doesn't matter where you start, because I'm going all the way around. I can start with a middle triangle. And I can say, that one's a 3. Then I go to this one, 3 again. Then I go to a square. Then I go to this square. Then I go to my last triangle to complete my loop. That's also okay. So it's not a row of things, it's a circle. And where I start that circle doesn't matter. The instructions are the same. Put 3 triangles and 2 squares together. Doesn't matter.
So you do that for every like vertex point?
They're all the same.
So
it doesn't matter.
What about line number 2? Like you have like can you repeat?
This line?
Yeah. So no further down.
This line?
That line. So
Look at that one. 3 triangles and a square and 2
so
squares.
even though there's like 2 full blocks and then there's like some leftover, you can just reuse.
Oh, I get
Where are the leftovers?
Okay, so
2 full blocks.
okay, so go over one. Right there. So
No, that's
right
not a
there,
full. That's
you
not a
have
full.
one more over.
Oh, this one?
So you have all that circle.
Yeah.
And you go over 2.
This one?
Yeah. You have that circle, right?
Yeah.
So now if you go over 1, you're reusing something.
This one?
Can you
Oh no, it doesn't matter.
It doesn't matter?
No.
Okay.
No. Still, at a point, 3 triangles and 2 squares have to come together. It could be ones that already are there.
So we
Yes.
can recount as long as they fit in.
Yes, because it's a different vertex for that triangle.
Oh, okay.
This triangle where the arrow is, the left one is for the left connection. The right corner point is for the right connection.
Okay.
I can't use the same corner point, sure. But there are different ones of them. Yeah. So no, it's fine. And they're all the same, so I can really focus on whichever one is convenient. What about the red tessellations? Pick anyone you want. What would you say is a vertex figure name for that tessellation that gives you instructions for how to make it? Not silent.
6 3 6
Oh.
3.
6 3 6 3. Who agrees with that? No
Oh,
one.
wait, no.
I don't know. It's a good guess.
It's 6.
So let's suppose I look at this point.
6 with 6 3.
Hold on. I'm verifying hers. Let's suppose I look at this point, and I decide to start with this hexagon. 6, then a triangle, 3, then a hexagon, 6, then a triangle, 3, and my loop is closed. So it's perfect. Doesn't matter where you start. It doesn't matter which point you're looking at, as long as you go all the way around. They're all the same. Sorry, I keep interrupting. Oh. You didn't have to look at that point, but make sure you look at a full loop, right? These two, the diagram doesn't extend, so don't look at that point. Look at one that is closed.
So we're doing this on the assumption that the diagram extends.
The diagram extends infinitely. But we don't have to show all of them. And there are, of course, others. You can start with a 3. 3, 6, 3, 6 would also be perfectly fine. Depends on how you want to go around it. But regardless, there are 2 triangles and 2 hexagons alternating. Doesn't matter how you write it, that's still the structure of the tessellation. Any other thoughts or questions on that? Let us go full screen again. That's where we were. Okay, so now the question is, then of course, We saw with the regular tessellations, there are only 3. If we then, okay, now we understand semi-regular tessellations. If we then ask, how many of those are there? Those floor tile arrangements are semi-regular tessellations because they're using regular polygons and more than one of them. The right one is the red one we just saw. It's the same. It's the same as the red one, isn't it? It's the same. No? The left one has a pentagon, a couple of squares, and a triangle. That's a new one. Hexagon. The left tessellation. So that's a different semi-regular tessellation. So you then ask, well, how many of these are possible? Turns out there are 8 of them. No more, no less. 8 of them. Because I'm allowing some more variety, I'm going to get more of them. What are they? There are the first 4. Ignore those things in brackets. That shouldn't be there anymore. You see the vertex figure name there as well. Let me see if I can zoom in a touch. Don't worry about the TE thing. That's something on Wikipedia that is completely different. Not for us. So I see on the left I have some octagon action with a square. The square gap we saw. I can now put a square in there. And I get a 4 and 2 8s. I can still have 3 triangles and a square, and 2 squares, but in a different arrangement, giving me a different tessellation. Then the third one we have seen. The last one on this page, there's another one that we have not seen. And then we have 4 more. Using a 12-sided polygon. And a little teeny triangle to fill in the gap. Which we can look at our interior angles and see that gap is exactly 60 degrees. And then there's another blue 12-sided polygon with something else. And then there's a hexagon and a hexagon one again. So, do you have to know all the regular tessellations? Yes or no? Yes. There are only 3 of them. Do you have to know all the semi-regular tessellations? No. You have to know some of them. You choose which ones are your favorite. So I could ask. I'm not going to ask the blue ones because I can't draw them without it looking like a circle. So I don't expect you to. The question could be, give a semi-regular tessellation that uses a square, or a square and a triangle, and its vertex figure name. So you might like this one.
Would you not give us a vertex figure name?
No, you have to give the vertex figure name. Or you might like this one, or depending on the requirements of the shape. Give a semi-regular tessellation that has an octagon in it. Well, it's only that one. But you do not have to remember the blue guys.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.